Assalamualaikum students. So before we jump into chapter 3, let's look at this slide, this statement here. Water boils at 100 degrees Celsius. Okay, is this statement correct? So if you recall back chapter 2, this statement is actually incomplete. A complete and correct statement would be water boils at 100 degrees Celsius and 1 atm. You need to mention both temperature and pressure, because as you have learned, at different pressure you will have different saturated temperature or boiling point of water. So remember to mention both temperature and pressure whenever you are dealing with this kind of statement. So we move into chapter 3. So in chapter 3, you basically will learn about heat and work. And in this lecture, you will specifically talk about heat. You can consider this as an introductory topic for you, okay, as you will learn more detail about heat transfer and equipment in part 4 next semester in CHE144. So basically, into the lecture, you will, by the end of this lecture, you will be able to define the concept of heat, the terminology associated with energy transfer by heat, and we also discuss 3 mechanisms of heat transfer. First one is conduction, second is convection, and the third one is radiation. Okay, so what is heat? Heat is a form of energy that is transferred across boundary of a system. Okay, it must cross the boundary of the system by virtue of a temperature difference, and it always from high temperature to lower temperature. So here they give you an example of 3 soda can with 3 different temperature, initial temperature, and it is exposed to ambient temperature at 25 degrees Celsius. So if you look at the first soda can, where you have equal temperature of soda can and also the ambient room temperature, so that means there is no heat transfer. While for the second soda can, if the initial temperature of your soda can is initially at 15 degrees Celsius, so you will need to input 8 joule per second of heat, okay, to warm up this soda can to up to 25 degrees Celsius. And you even need to input a higher amount of heat energy, 60 joule per second, if your initial temperature is even lower, 5 degrees Celsius in this case. So we can see that heat is energy in transition. It is recognized only as it crosses the boundary of a system. So here, imagine you have a hot baked potato that you just took out from your oven and let it cool down at your kitchen. Okay, expose it to surrounding air. So initially, your hot baked potato contains 2 kilojoule of thermal energy, and as you cool it down, you are actually transferring 2 kilojoule of heat to the surrounding, and at the end, your surrounding will receive 2 kilojoule of thermal energy from that hot baked potato, which is now cooler. And when we're dealing with heat, okay, we will see this adiabatic term. Okay, adiabatic process means that the process during which there is no heat transfer, your Q equal to 0. So how we can see this? Okay, it can be under 2 conditions. First one is when your system is well insulated. That means there's no heat can go in or can go out because it's well insulated. Second condition is when both of your system and surrounding are at the same temperature, like the example that we talked just now in the previous slide on the soda can. When your soda can is at same temperature with your ambient temperature, 25 degrees Celsius, that means there's no heat transfer. So with that condition, we call it adiabatic process. Okay, now let's look at the mechanism of heat transfer. First is conduction. Conduction is the transfer of energy from more energetic particles of a substance to the adjacent. Keyword here is adjacent, less energetic one, as a result of interaction between particles. So conduction can actually occurs in all phases, solid, liquid and gases. In gases and liquids, conduction is due to the collision of molecules during their random motion. However, in solid, conduction is due to the combination effect of molecule vibration and in a lattice, and also the energy transport by free electrons. So here on your right side, a cold canned drink in a warm room will eventually get warmed up to the room temperature as the result of heat transfer from the room to the drinks through the aluminium can. So remember, energy is only transferred from high temperature to lower temperature. Okay, so when we deal with conduction, we will use this equation named as Fourier law of heat conduction, where Q conduction is equal to negative A kT. A is the area that is perpendicular to your heat flow. Okay, see this blue arrow? So blue arrow here is your heat flow. So the area is the one that is perpendicular to your heat flow. KT, the term KT is referring to the thermal conductivity of the material that you pass through, okay, in watt per meter Kelvin. You can get this K value in appendix. dt is the change of temperature, while dx is the length, okay? The length of the material that you pass through. So here in figure 2.2, it says indicating direction for heat transfer. It can be positive in a positive direction or negative in the negative direction. So you see here, it's always from hot to cold. It's just that the direction, if you do it from left, okay, from hot to cold, it become positive. Okay, it's positive X direction. Q equal to 500 watt. But if you go to the negative direction, Q become negative 500 watt. Okay, so besides this equation, you also can use Q equal, the one that I wrote here, Q equal to A kT, change in temperature and change in X. Later I'll show you what's the difference and how to use this positive and negative direction. So in this example, a flat wall is composed of 20 cm of brick having a thermal conductivity kT equal to 0.72 W per mK. The right face temperature, this is your wall, okay, and the right face temperature is 900 degrees Celsius, and the left face temperature of the brick is 20 degrees Celsius. So you need to determine the rate of heat conduction through the wall per unit area of the wall. So here, first you write down the Fourier law equation, and since the question asks you for rate of heat conduction per unit area, so you bring the A term to your left side. So you divide by A. So Q con over A equal to negative K over dt dx. Okay, so now the question already tells you which one on the right side and which one on the left side, and it always from a high temperature to lower temperature. So you're actually going to the negative direction. Okay, negative direction. So here K put negative 0.72 W per mK. T, your initial T is 900. So 900 minus 20. Okay, and your X 0.02 minus 0 because you're going to the negative direction. So with this equation, okay, plug in all this, including the negative sign at the front of K, your Q conduction over area is equal to negative 3168 W per meter squared. So it's negative in negative direction. So if you want to look on, you want to do the same example in positive direction. So same thing. You write the plug-in key, okay, and here, so positive direction is to your x side, to your x positive direction. So 20 minus 900, 0 minus 0.02 meters. Because it starts from 0 here, x1 is 0 minus 0.02 meter. I convert 20 cm to meter here. Okay, so your answer will be a positive 3168 watt per meter squared. So this is what it meant by positive in positive direction and negative in negative direction. Alright. So if you use the equation that I wrote at the bottom here, so you can actually omit the negative sign and just put delta T over delta X. Okay, change in T over change in X. And 0.72 K as 0.72 watt per meter Kelvin. Okay. 900 minus 20. Always take the high temperature minus the lowest temperature. And X is the length. So the length that you're interested in is 0.02 meter. So here you will get a positive answer. Q coin over area equals to 3168 watt per meter squared. So all these are correct. If you mention, okay, you need to mention what the direction that you look for if you use this equation. Okay, your answer will be negative is if you do it in negative direction, and your answer will be positive if you do it in positive direction. So I hope you can clearly see the difference here, and in the next video we will discuss on convection and radiation.